C++ class natures and their canonical form. When I submitted the selection of talks, this is one that came up. And the thing is, what is actually the meaning of canonical form? And this is my canonical form. I run around with these sets because I create the design, and they come from the WG21 meetings in Rapperswil that I hosted in the last decade, the 3 ones. And I have 3 heads left, so who's asking a very interesting question in the end or in the middle can get one. So the canonical form is a standard way of representation. We all might have heard of the rule of 3 when we programmed C++ in C++ 98 and on. Scott Meyer's rule how to write classes, and that was extended later on to the rule of 5 or 6, and that is part of the topic I want to show you today. And this is one of what, let's say, my IDE, for example, generates from me. If I ask, create a new class, example, I get a virtual destructor, I get copy constructor, a move constructor, a copy assignment, and a move assignment. And the question is that really canonical? Do all my classes have to look like that? Do I need all these operations? Do I need to define all these operations? And what would I do about that? And the question is, should I do something about that? For example, should I have a virtual destructor? And my claim is not always. But even if you define all these 6 operations, you might get naughty. And I've seen real life code with similar peculiarities that were really, really strange. And we had one in the standard as well. Someone remember auto pointer? That had exactly that kind of copy constructor with a non-const argument because it was actually mutating the thing that was passed in, or with the assignment operator the same, where this one is also like that. But there are also other interesting facts like, okay, a throwing destructor is not something you want to have. Or a move operation that might throw. This you can throw from moves, but you better do not. That is really evil. It's allowed by the syntax of the language, but you just get what you deserve. I've seen things like that. Okay, assignment operator that return void also happened in practice. Again, that is even discussable if that is not a too bad idea, sometimes. But at least an assignment operator returning an L-value reference that is called on a const object, so would actually require const cast to return star this. So a lot of things that are wrong here. This is not how you should program in C++, but this is, some people write code like that because they don't know better. That is actually why I give these talks and try to help people make it better. Even the implementation, some people say, okay, if I have to declare it, I want to implement that. And before we had C++11 with the defaulted operations, we had to implement it. And very common is if I have a base class, it's very easy to forget to copy actually the base part of the object. That's really something that we can forget. And the typical default is to copy all member variables. And should we actually do that? The compiler is much better at providing that, and the compiler will not forget to copy the base part. Anybody had that error of forgetting the base part? Some nods? Okay. There are even more non-canonical things. Okay, I can pass in an L-value reference to my copy assignment, and that's a perfect copy assignment operator, will automatically chosen by the compiler when I use assignment. And it allows me to actually modify the right-hand side of the assignment operator. There might be domain-specific languages where you do things like that, but that's not how you should write regular classes in your C++ world. So don't do that. And whenever I have some reddish background on code, that's not what you should take home. And then there are other guidelines that say, okay, if you have an operation, please spell out the operation and set equals default, because then you get at least the compiler provided version that presumably are correct. And this is what you then get told to write. You write, okay, you might make a constructor, a default constructor, a destructor, copy and move assignment operations, and all what the compiler would provide. And depending what's else in the class, it's not really interesting that the compiler provides all these things. And defining them actually makes your class worse, because you actually reading all these operations and figuring out if there isn't a bug where you actually might have forgotten const or forgotten no except or used something else slightly odd. It's really hard to figure that out, especially if you have hundreds of classes in your system or even thousands and all classes look like that. One minor typo, e.g. a copy-paste problem, where the argument of the copy constructor is not the actual class. Before it's actually used, you never recognize that. And you might even still get the copy constructor provided by the compiler, but not the thing that you're writing down there. So my guideline when I write code is omit needless code, because you don't have to read that. It might even lead to faster compiles because it's less to parse, but at least it allows us to concentrate on the important parts. So there's a saying by my friend Kevlin Henney, and I borrowed that from him: less code equals more software. It's not only about compilation speed, it's about the mental hurdles we have to take to understand what's written down. And the fewer things are written down and all the implicit mechanics are considered provided, that is how you actually write code. We no longer do machine language or assembly language most of the time. We just assume that the compiler generates the code we want to get. And that's important. But that also requires that you learn what's going on under the hood, or at least appreciate what's going on under the hood, and just take it for granted. Anybody seen the video or the talk by Howard Hinnant where this table was explained by him at ACCU 2014? Seen that? Highly recommended. Go there, look that up. ACCU 2014. A detailed explanation what special member functions you get when you define one of the other special member functions. And that's really important knowledge. The problem is, when I ask Howard, well, why don't people just appreciate that? Well, it's too hard to remember, or too hard to always consider what's going on underneath. And that's why I actually made other talks and this talk, to actually not have to always consider all these entries in this table to figure out what's bad about it. So there are some glitches. The red parts there in the center is, you still get destructor and copy constructors even if you define one of them. And that can be really problematic, because when you define a destructor, you usually have some interesting things happening in the destructor. And that means that the compiler provided copy operations might just be wrong. For move operations, it was defined correctly in C++11. You don't get a move operation when you define a destructor, just as one of the examples. But you still get copy, and the compiler provided ones might just be wrong. But I don't want to go to repeat Howard's talk. I want to give more insight. What's a class nature? It's not about the mountains that we see from our hotel windows maybe, or the planes that are also visible here in Denver. No, it's the kind or the character of a thing. So I might be a bald guy. That's one of my natures. But I'm not the only one. But I might have similar problems as other bald guys. If we go out in sunshine, we better wear a hat. So that might resemble our character or our essence, that we have to wear a hat, otherwise we would get a sunburn, which is not very pleasant on the skull, and maybe not even healthy. So that's the class nature. What is actually the essence of our classes that we write? And very often this is not, let's say, in a lot of, let's say, naively written code, sometimes it's not clear what is actually that class nature. I'm not talking about the purpose. I'm talking about, okay, is it really a value type or something else? Is it a pointer type, a smarter pointer type or not? And I try to figure out what are the essential natures that we have to deal with. And I tried that last year and came up with this mess. If you want to understand what's on that slide, watch my video from last year. I tried to do better this year. That's why I actually provide that talk. It's all about, okay, what are the things where you shouldn't go and what are the nice areas? And we have the nice area about value types up here where everything is fine and smooth and some weird combinations down there. And I don't want to be more constructive. Can we make that better to see the underlying class natures? And sometimes you have to say, you have to combine natures. So I'm not only bald, but also wearing a nice jacket today for this video. Other people are bald and wear a t-shirt. That's also okay, but we share commonalities and we have difference. And if a t-shirt guy would actually borrow my jacket, he would look like wearing a jacket with a bald guy. Okay, what can we make to see the class natures? And I came up with a list of 4 interesting natures, and I made up a name for one thing that I wanted to point, and Sean Parent had a better name for that, but I already forgot what he talked about that. So let's see. Value types. Who has an underlying understanding what a value type might be? Some. Who has never heard of the concept of value type? A value type is something, if you consider a value itself, the number 42, it exists out of time and space. And a value type is representing these kind of concepts where, okay, I have a variable that might have the value of 42, but the value 42 is kind of ephemeral. It's there, regardless of the bit pattern. We have bit patterns representing 42 in our language, but a value type is about things, it's there, and if you copy it, that's one of the essential things, the other object has the same value. It is indistinguishable except for its address from the original value. And the original is not changed. That is also part of the keynote where Sean Parent actually was explaining what actually a value is. Then a lot of fuss was made in the 1990s when I learned C++ about object-oriented programming. Object-oriented programming was so fancy because I could write code using an abstraction and then use a different implementation of that abstraction with the same identical code, and it would just work. That's called dynamic polymorphism. And in C++, one of the mechanics to implement that is virtual member functions. And this allows us to have, let's say, a common abstract interface and then have different implementations. And the mechanics to achieve that is inheritance. And a lot of inheritance is the root of evil. Again, citing Sean Parent. I believe Sean Parent had said that as well. So the polymorphic types is, I want at runtime the flexibility to have different things under the same abstraction and use it similarly. And that's really an important, it's at runtime. We have other mechanics where we can actually have compile time flexibility. Go look at Andrei Alexandrescu's seminal book, Modern C++ Design, where everything is made by policy-based design. We have templates, and then we generate just simple types from that. And then we have 2 things where I made up the names. I call it now designating types. I used to call it pointing types or pointer types or reference types or referring types. And the problem is all these names are more or less overloaded, and they might presume that we have a pointer or a reference. But there's a whole category, a kind, a nature of types that actually are referring to something else and are invalid if that something else is not there. And if I copy an object of such a designating type, the copy might be trivial and it might be it will refer to the same underlying box there, and if the box disappears, the designating types would become dangling, invalid, and no longer be useful correctly and leading to undefined behavior, which is something we don't want to have. And that's a big danger of these designating types. On the other hand, they are really the key issue to get performance, to write interesting data structures and so on. But you better don't have your users deal too much with these designating types without being aware of that they are designating types. And I have another talk I gave about 2 weeks ago at NDC Tech Town that will be available on video, where I talk about half an hour on how to deal with these designating types. And the last category is, that's why I'm wearing this jacket, is the managing types. And managing types manage resources that could be memory, that could be other objects, that could be external resources like a file handle. A classical managing type is a file stream, fstream object that manages the connection to the outside world of the operating system. And the interesting part about managing types, they have an interesting destructor implementation with side effects. You all might have heard of RAII, or scope-based resource management. Managing types are those types that do something interesting in their destructor. And that's how you can actually figure out what they are doing, that they are managing types. Now, again, designating is not owning. What are examples for designating types? It's a pointer, a reference. Iterators are designating types. Views are designating types. Span is a designating types. All objects of these kind of types have the potential to dangle, to be invalid. A value object can never be invalid. It always has the value, regardless. And these designating types, that is one of the curses of using our language, because it's so easy to make a mistake by using it while it's invalid. And that's really something where you can hang yourself. So remember, these types are really where you have to put on your superhero suit and be very careful in handling things, because they allow us great power, high performance, but also give us a lot of responsibility. There's a question, yes?
Is weak pointer designating type?
Weak pointer a designating type? I would say I have a separate category for these things. Stay tuned. I wouldn't say it's a designating type, because it's at least you can recognize if it's dangling. You can still misuse it, but if it's not, you can see if it's still useful or not. It's not silently dangling like a plain pointer. So weak pointer is somehow not actually a designating type. It's more like a managing type. And if you look at a destructor of weak pointer, you will see why. So remember, the validity of a designating type depends on another object that is not managed by it. And you have no chance to figure out if your designating object is still valid by itself. Now, we can use all these class natures as other, in different contexts, as a member variable, as a base class and a parameter. And there's a question again.
Yeah, about the iterators?
Sorry, I can't hear you.
About the iterators?
Yeah.
Not all iterators are non-homogeneous. Some lazy iterators, like recursive direct operators.
I'm talking about the iterators the standard library provides today. I'm not talking about where you implement the iterator concept with something else, with the manager, for example. So we can use them in all kinds of situations. And for example, a designating type, or let's look at the different things. I have some. A value type as member, check. Nothing bad happens. Your class using a value type as member is still valid. As base class, a value type as a base class, you should see some blurred names here, but the contrast on the projector is not good enough. So if you have a base type, a value type as a base type is kind of an odd thing. There are a few situations where it can make sense, and I have an example right now. But a value type as a parameter, perfect, nothing bad happens, all the compiler mechanic is good. As a return type, nothing bad happens, good. Now if you look at, that's an example for a value type as a base type. Adapters, that is where you might actually inherit from a value type, typically privately, and provide a specific reduced set of operations, and the inheriting constructors make this really attractive from C++11 on, where you can actually get all the constructors of your base type, even if it's a private inheritance. The thing what you should take care of, not adding data members. Especially if you don't do private inheritance but public inheritance, for example, to extend your base type with additional operations, like indexing for a standard set with an index operator, to write, let's say, bad for loops with it. This might be something where you actually want to prevent slicing and want to not add data members to the subclass. Now, polymorphic types, as a member, to actually get polymorphism, you have to use a designating type. You have to keep them around as a reference or a pointer or whatever. Unless you actually use a managing type like unique pointer to keep the polymorphic object as a member, then it's okay. As base class, that's what they intend to be used for. As a parameter type, again, you have to use a designating type to get the polymorphism in the called function. And as a return type, you have to use a designating type, but then you get the problem, who owns what's returned? And that's where smart pointers can come in to return, let's say, a unique pointer to the base class to actually transfer the ownership with the return in a polymorphic way. If you look at designating type, if you have a member variable that's a designating type, and that's contagious. It's like a virus that spreads. So if we have things, I want to have a view member or a span or a string view member in my class, then your class implicitly becomes a designating type because it depends on some other object that it doesn't control. At least if you just do it naively. If you look at smart pointers, they contain a designating type. They contain a plain pointer. But they actually managed it, so that's the next category. And they actually use designating types, encapsulate it, and don't leak that, and have the interesting operations to make them just work. Most designating types are not suited for base classes, especially if they are built-ins like pointers and references. It's very typical to have them as parameters, and passing something down the call chain via a designating type is one of the powers where it's safe to use them. Unless you start a thread or a coroutine there. And as a return type, we have the problem, is it dangling or not? And if it's not managing, the question is, who takes the responsibility of the referred to object? And if you look at managing types, there are some interesting things I will show you. It depends what's actually valid. Sometimes you might use them as a base class, for example, as an adapter. You might use them as a member, but it depends managers come in different flavors. So we have that kind of a manager, but we also have different flavors, and we see that in a couple of minutes. And as a parameter, you usually would pass them by reference, and we will see that because if you manage something, you don't want to copy all the infrastructure that you're managing. That's why you typically pass them as a reference. And let's look at the question mark later. If you look at these properties, the most versatile thing, and the winner is actually value. Right? Design your system around value types and make sure that most of the stuff that you're actually handling is a value type. Then your users don't have to care about it. It doesn't mean that the others are completely unnecessary, but if you, let's say, make everything an OO base class and allocate on the heap, that's the code style people learned in the 90s and some people still use. Oh, I have to write new when I have a class. In Java, yes, but not in C++. Don't do that. So what are the canonical forms of our 4 different categories that I created? If you look, canonical form, what does that mean? One of the properties that we might get is, okay, we have for value type regular, the concept of regular type. Sean Parent explained that today in the keynote. If it's copyable and the copies are independent of each other, then and still compare equal, that's what makes type regular. It's not unique. That's a feature you might learn from unique pointer or unique lock, where you have a unique representation holding the ownership of something. Values don't own anything directly, or they are not owners of something if they are not also something else. You will not have the unique part. And they are proper. You can just use them, and they are not actually sharing something. It's just copying around, and that's good. And the good thing with the value types, all the defaults just work. Even if you encapsulate them as a private member, the default constructor is just working well. And I put that only in because I presume that a value that has a value type that has a private member has other constructors that actually create some, guarantee some invariance or whatever, initialize the member accordingly to what's given as a constructor parameter. Question?
Will it be zero initialized? Well,
this will be value initialized. And this means it will be 0, yes. And that's a mistake by me. I should have put in the default member initializer here as well, to make sure it's not true. It's not it's not uninitialized. Yeah.
By having a default constructor that's visible, aren't you sort of committing yourself to two-phase initialization with your value type? And isn't it frequently desirable to avoid that?
Okay, this is the question is, why do I do a default constructor? And the question is valid, and the assumption is also valid. Okay, if I commit my type to be default constructible, does it actually have a default value? And I would say value types should be default constructible because that's part of regular. You don't want to have to specify a value whenever you default construct them. But again, if your type has interesting, let's say, interesting initial conditions or class invariance, then you might opt to not have a default constructor and still be kind of a value type that's not exactly regular but good enough for you. So that's possible.
Could I ask a follow-up to that, which is, suppose you have a class with several value types as members, members of value type, different value types. The interior value types might be default constructible, but is it necessarily the case that you're going to get the correct default construction at the higher level? In other words, maybe the higher level thing simply isn't default constructible, or do you just block that at that level at that point?
So the question is, if I combine several value types as member, Some of them might be default constructible and some not. Could I get a default constructor? You don't. But that's not a good practice to do. That would be an oddball. If you have value types and members, provide non-static data member initializers to make sure that they are initialized correctly. Now, polymorphic types. Inheritance is the base class of evil. Maybe it was Andre who said that. Even the keynote by Bjarne Strostrup this week showed how you can actually get rid of dynamic polymorphism and virtual by using other things. So it's very often overused. Virtual is overused. It's really very often a rare case that you at runtime have an open, or let's say, that you have an open set of possible extensions that you want to future plugins without changing existing code just to work. It happens to be the case that's very common in UI design, in UI frameworks. That's where it makes sense. But even there, I'm still waiting for a UI framework that is not relying on object too much, that actually has real containment. And again, it's often overused, and very often you get bloated APIs because people don't get the right abstraction, that is too broad or too narrow. And then you have to downcast, and every cast in your system is a potential design problem. I don't say you should never cast, but whenever I need to cast it somewhere else, to something else, consider this, I made it I have a problem in my design. It might not be worth to care about it, but it is a problem. A good OO base class is non-copyable to prevent slicing, which is again where the defaults get it wrong if you don't pay attention. That's where the rule of 3 came in. It might be managed by unique pointers. It might not be a proper type because you might not be able to actually create an object of the base class type. It might be might have pure virtual member functions, so you cannot instantiate it. It might be managed by a shared pointer or some other things. And it's very often not regular. You cannot copy a polymorphic object and assume that at the target the correct value appear and that they are independent. Another question.
Your polymorphic nature, the derived class, are you treating that as necessarily not having a polymorphic nature? Because some of the things you're saying here seem to apply to the base class.
Let's say, if the question is, what about the derived class with the polymorphic nature? I would say derived classes with the common base class are in the same boat. And you might get around and, if I know it's this subtype, I can copy it and then I get the same subtype. There's even a proposal in flight for the standard library to have a kind of smart pointer that deep copies object in a polymorphic hierarchy called, I think the current name is polymorphic value. It changed its name over the time. And I think that's a design aspect where I believe people are very often misled. It's an area where if you really, really can prove that you want it, do it, but it's not something you should come up firsthand. And I would like to continue. Can we take those questions later on? Otherwise, I would not be able to finish in time. So how is my canonical form that I suggest for OO base classes? You must have a virtual destructor that we learned from since. And you better don't unintentionally get the copy operations. Remember that table I showed you? Okay. Even if you define a destructor or declare it, you still get copy operations. And that's where slicing comes in, the silent slicing that comes in. And taking my hat on, the minimum amount of code to write to get rid of the copy operations by still being able to have a default constructor. I looked at the table from Howard, and I came up, okay, if I delete the move assignment operator, I no longer get a move constructor, and I automatically get no copy constructor and no copy assignment operator. So deleting the move assignment gives me exactly what I want. So my base class is non-copyable, non-movable, and it's okay to be that way because I don't want to copy it, because it will slice if I have a subclass instead. And I nicknamed it after some thoughts and called it the rule of DesDeMovA. And if you look my ACCU 2019 talk, I give some motivation how I came up with that and what is that. And if you apply that, you get the shortest version of a base class that is intended to be as correct as possible at the moment. Now, there are other means to get polymorphic mechanism. Bjarne took one, okay, if you have a fixed set of variations, we have now a standard library type, and we had a similar type in the Boost library before called variant. Put all your variations in variant, and that's it. Put them in a box, and then choose one and write your code against variant, which is not that easy. The other option is actually never get to the idea where you actually leak polymorphic types, but have a concept interface where you do type erasure and heap allocation hidden behind the scenes to get this flexibility of polymorphic types. So you have virtual somewhere, but nobody sees it. And that's talks by Sean Parent. And that requires heap allocation, or sometimes you can get around with it with small object optimizations to avoid extra heap allocations. Depending how big your objects are, even Bjarne said on Monday, okay, variant works best if all your variations are actually about the same size. Otherwise, you get a lot of potentially bloat from variant. Now, if we use designating types, that's a question, what happens there? Some of the designating types are actually perfectly regular. You can copy a designating object, and the copy is identically. It refers to the same original, and it's indistinguishable. And if you look at string view, span, a pointer, it's just what they do. But they are not value types. That's the important part. There's one oddball, that's reference types. They are not regular because you cannot easily copy a reference. And if you have it as a member, you get some interesting things. The big problem with designating types, so shy away from them unless you know how to deal them and unless you don't leak them, is they can be potentially dangling. And to get rid of the problem with references, as a member, we have the reference wrapper in the standard library to make your class still being assignable and regular, even if it holds reference logically. So the biggest thing, who's not using T-star pointers, plain pointers? A very few, not using. Who's using pointers last week? About the same. Who has used pointers in his or her life? All. Okay, so some people try to shy away from pointers, and they are those who know that they are not superheroes. Dealing well with pointers requires superhero powers, and that's where we actually have to watch out for. It's not impossible, and we need them. It gives us a power in C++, but please don't make your users of your code have to deal with plain pointers, especially if your users come from C, where pointers are everything. So, alternatives: use values, only use a pointer in a local scope, or manage what it's pointing to. Instead, use a manager like unique pointer, or encapsulate things like, oh, I want to unique pointer also encapsulates a plain pointer to actually not leak what's down there. And this again is a table from my talk 2 weeks ago at NDC Tech Town where I explained it in deep. That's more or less showing you kind of a flowchart or selection possibility. Okay, I have something that is a pointer or a designating type, and then there are different questions I have to ask myself, and then there are different suggestions how to get rid of T star and use something else. And one of them is just use a value, others is use a managing thing, use an optional, a reference, and other things. And there's a yellowish area in the bottom where there is something missing in the standard library and where we might have to work around to get that right. And people do that. Now, one of the big problems, if I have a designating type, unfortunately my shading is not working well on the projection. I'm not sure how that will turn up on the video. The big problem is with the, so look at the slides when I upload them, is returning a designating type. When you're writing C code and you have a designating, the function returns a pointer, you never know what you have to do with that pointer. You have to read the specification of the function or read the code of the function to figure out what's going on, what's wrong with it. Or do I need to take ownership or not? And the core guidelines say, okay, we want to have that owner template to mark ownership. That's wrong. If you have something that takes ownership, use unique pointer, full stop. Owner T of core guidelines is not good. And you have interesting things that can happen. You can return star this from a class. And if the member function is not ref qualified, you can call it on the temporary object, return this pointer as reference, and it becomes immediately dangling because at the end of the statement, the temporary object is destroyed. It's not lifetime extended because I got it from indirectly, and I have interesting things that go on. Even the standard library classes have things that return designating types like .begin or .data or .cster. You can call them on temporary objects, and if you think you have still something valid around, you don't. Ranges try to protect you a little bit from that, but that gives you other problems. You always have to have an L value to keep the original range that you want to have around. And remember, .get of your smart pointers breaks the encapsulation. Whenever you see .get, put out a Lycra suit, wear your mask, and become the superhero to deal with what you got. So, how can we fix that? If you ref qualify our member functions, they no longer can be applied to temporaries, at least not if it's an L value reference. And that helps a lot, so code like that would no longer compile. But even in the standard library, we cannot fix that yet. Maybe that's a task for C++26 or so, to get the defaults for the for the assignment operators and for all the member functions that return some of the guts from inside an object ref qualified. So, if you have a member function that returns a designating type, and the designating type refers to something that's part of star this, ref qualify that member function, because then you avoid the immediate dangling on temporaries. Example, even the compiler generates wrong code for you because the defaulted assignment operator, again, returns star this. And if you bind a reference to that, you bind a reference to what's no longer there when you use it. So what you should do actually, if you define your own assignment operator, mark ref qualified. It's still red because I don't recommend that you do that because it's too odd to do it. But it might be something you have to consider, especially if you actually implement your assignment operator. You might want to make it more future-proof by providing that ref qualifier there. So if you look at that exactly, we might be better, I hope that my animation works here, to actually put the ref qualifiers there. The question, it's not yet better because it's too odd for people to recognize. But if you don't do the default version and implement your own, then it might be actually the thing that you want to get. Designation is contagious. So when you have a designating member variable, be careful. Managers. So I look like a manager today. I used to be one. And I'm running out of time, but I'm hurrying up. I showed you that. It depends how you use them, if it makes sense. Managers are the powerful things, and the curly brace closing and having the destructor is what makes managing objects so powerful and important. That's one of the key things of C++. And the class nature manager actually spreads out in different aspects. We can have non-copyable managers, like scope lock, which you cannot copy. You use it locally to manage and have an interesting side effect in the destructor. We have managers that are unique because the ownership is unique. That is what you would use if you have a resource that's not easily copyable. And we're having two versions of that resource might get you into problems. Unique pointer, unique lock are examples. The question is, can we have proper manager types? Can we make them regular? And yes, we can. It just requires superhero powers, or at least diligence, to do it right. Standard vector is one of those managing types that is also a value type, which is good. We don't have to care. We just use vector and it works. So, scope manager, check, good. Unique requires a little bit of work. And there's a question, should I do shared managing object? We have shared pointer. If you consider shared pointer a good idea, go to one of Nico Yosuti's talks where he blames about it. And the only thing that is good if you use shared pointer tconst, because that gets you almost value semantics with an optimization of not having to copy big things around. And you can have value managers as value types, but that requires work. So if you look at a scope manager, that's one you don't want to copy. You have to define a destructor because otherwise it wouldn't be a manager with an interesting effect. Usually the constructor acquires the resource, the destructor releases the resource, and you apply my rule of DesDeMovA to actually get rid of the potential copying that would actually make the resource wrongly, because the resource typically is a handle, and if you copy the handle and delete or release it twice, that's where bad things happen. A unique manager has a specific aspect. If it's unique, you must care for a moved from state that is distinguishable from all the other possible states of your resource. Because a unique managing object in a moved from state, you don't want to have the side effects in the destructor. You don't want to release a resource because it's no longer there. So you have to distinguish that. And that's one thing people get wrong, because unique pointer is okay because the null pointer is a perfectly moved from state. It also provides us a default version of the default construction of a unique manager. A scope manager usually cannot default construct unless it's a single purpose thing. So a default constructed unique manager will be in the moved from state. And even the standard says something about valid but unspecified. I believe if you actually have a managing type, you want to have that specific moved from state so you don't release your resource twice in the destructors. So we have to define a move assignment and move constructor and the destructor. And this gives us no copy operations. But you have to make sure that you actually move around the resource when you move. And one possible implementation is we have the destructor that has this interesting side effect. we have the destructor that does this. I extracted the release that checks if the resource is valid and then actually resets it, and it should actually, that's the optional reset, so it's empty afterwards. And if we look at the copy assignment, for example, if it's not the other, so if we're not, let's say, releasing ourselves, we release this object because it's now overwritten, and we swap our resources and are done. So that's, let's say, a canonical point of view, how to implement unique manager objects with my guideline. And the move constructor is very similar. There we don't have to destroy something, sorry. No. That's when you have too many animations on a single side. We don't have to destroy something because they haven't constructed one yet. But we have to have the side effect on the other resource to actually reset it, because that's where we no longer own the resource that was there. Sharing is hard. Don't go there. Especially in a kind of multi-threading, sharing is horrible, and getting the synchronization right is really terrible. Even with shared pointer, only the counters are synchronized as atomics. All the object that we refer to is not synchronized. So be very, very careful. I changed my mind over the years. Yes, I learned. If you want to have something where you share something implemented using shared pointer, then at least the reference count is not wrong. And provide concurrency control. And that's really hard. Don't do that. Now to the superhero part of managers. I'm not talking about CEOs, I'm talking about techies. Manager as a value type requires us to apply the rule of 6. To implement all these operations sanely, it's hard, it's doable, but it can be rewarding because then your type is actually safe to use everywhere. It might not be the best performance, so that's where optimization kicks in, but usability of your type and the safety of usage, having all these operations correctly is good. So you have to have a copy operation where the resource, but to actually be able to do that, it means that your resource has to be copyable. It has to be clonable. And that's important to know, otherwise it would not go. And if you want to make it future-proof, because you have to implement the assignment operators, don't forget the ref qualification, then it wouldn't be callable on temporaries, and you wouldn't get the effect that you have a non-L value where you return an L value reference to. Now, quick quiz. Standard vector is a manager and value, depending on what T is. Scope log is a manager, what kind? What subkind? A scope manager. It says so. Unique pointer is not a designating type. It's a manager type. It owns its thing. It has pointer in its name. That's why I didn't use pointer. It's designating type. It actually, it's not a designating type, even though it's pointer in its name. It's a managing type because it has a destructor with a side effect and it owns what it's referring to. It's an owning thing. It's a managing type, not a designating type. It cannot become invalid by someone else taking away the pointed to object because you cannot take it away. It's only null then. Shared pointer, tconst is? It's a managing object that happens to behave like a value type. An optimized value type, but that's tricky. And thread? Thread is an oddball. That's the thing, that these things are typically in Bavaria, it's Wolpertinger. It's when a non-Bavarian goes there, they tell you how to hunt them, which is requires a lot of schnapps and stuff like that. But they are still oddballs and we have to live with them, but be careful about them and be conscious about them. And with JThread, we will get a managing thread object in C++20. So, as member, almost all is fine. Take care about designating types and be aware of the different variations of managing types and make things as valuable as possible. This is a table where I try to summarize again what special member functions you actually see, the canonical forms and what to do. And if you look at value, the defaults are typically, so the gray part are the nice things, everything that's gray, it's very easy to, you don't have to think about. That's good. Not having to think about is very good. It just works. You have the reddish one, the designating types. They are useful, but be very careful, especially because they very often are just regular copyable, and that means they are contagious everywhere, and make sure that they are no longer used when the actually object they refer to is gone. We have our 3 categories of managers. Scope managers are very easy to implement. You implement the destructor because that's why you manage something, and you delete the move assignment, get rid of the other things, you don't have to think about them. A unique manager is a bit more involved. I think with my optional guideline, it helps you to have things where you might don't have a type that has a special illegal or independent type. For if you would have a unique manager for, let's say, file handles, their -1 is a typical error state that you can use. Okay, if it's -1, I know it's moved from, and you could set that. Better not 0. And if you want a value type that manages stuff, better use one, like use an existing manager and wrap it. Like take a vector member to manage large amounts of data. But if you have more things to manage, then you might have to implement all these operations yourself and do it. And OO-based classes are almost on the oddball side, in my opinion, in modern C++ code. If you really need to do that, very consciously design it, make a good abstraction, and really know if you have to have dynamic extendability in the sense of I need to extend my subclasses to a common base class. And there are other options to get similar effects. Member variables will make things also interesting. Values, everything is fine. Scope manager, nothing bad can happen, as you're more or less, everything just works. The problem is it's contagious. So actually, if you have a scope manager as a member, your class also becomes a scope manager. If you have a unique manager as a member, your class becomes also a unique manager by default. It's no longer copyable. If you have a designating type as a member, pull on your superhero suit, because your class type also becomes a designating type. And you have tref, which is a sub-version of the designating type, and you even get the benefit of no longer being able to assign to that object and no longer be able to default construct it. You can remedy the assignment operators by using reference wrapper instead of tref. So these are the influences of the natures. Takeaways. Be conscious of your class nature. Take it as a how do you say that? A toolbox for your design in C++. Select your special member functions according to the nature and best to the canonical form. Be conscious if you have to step away from that and make it explicit and maybe even explain why you do that. Values rules. And beware of designating types that come as disguise as a class type. And minimizing the surprising class natures. Don't write unicorns everywhere. It makes it very hard to deal with your code. And we are done. And I think we had overrun last section, and there's break afterwards. Feel free to ask more questions.
Thanks for another great talk. Some of your
slides will be things that I print and pin to the wall, I think. So thank you, very valuable. I have a question. How do we get from where we are to there?
Say it again.
How do we get from where we are to there? So you're dealing with an existing code base, a legacy code base, old code base, where we've got lots of things, pathological natures out there. So for example, we have a lot of polymorphic types with that don't satisfy Liskov substitutability. What's the path? Do we have, or at least are there resources?
I would say write unit tests against your code, refactor mercilessly, and you might actually employ cdevelop to do so because it's one of the IDEs that implements C++ refactoring.
Okay, thank you.
And I'm supposed to stop right now, maybe because the video would take so long. I'm happy around until tomorrow evening or even until Saturday, so grab me and ask questions or send me an email. Thank you a lot. Bye-bye.